TAs are behind. Let's see what they got up their sleeve here. All right, they definitely have a strategy going here. That's 3 points. There's not much option left for you guys. Yeah?
Choose the right.
Yeah. No. That'll be a 0. All right, that gave you a point. 2 went to 1 and 1, 1 point. Not a lot of choice for you guys either, I guess. There's only one way to split that stack. All right, 2 points. And your final move for the class and all the candy, you get 1 more point. Let's see what your total is. You got 22, 24, 26, 27, 28. And the TAs are going to get one last move for the TAs. All right, and you got 2, 1, 1, 2. Oh, that's interesting. 1, 2, 3, 4, 5, 6, 7. What? That's 7 times 8 over 2. 50. No, that's not right. Did I do that right? Oh, 28. We got a tie. Ah, jeez. All right. I tell you what, I'll give you guys one more chance to start over. You've seen that. You got to beat them. You tied them. You got to beat them. One more chance here. You got to beat them, though. You got 28. You already tied them. They came from behind and tied you. You got to beat them. You got off to a good start, but then they caught up. Oh, now your class reps had an interesting thought here. They asked, is it possible that any strategy gives 28? I wouldn't do that to you, would I? Yeah, probably. Any ideas? Can you beat 28? They're already eating the candy. In fact, you can't beat 28, and you can't do worse than 28 either, because every strategy gives 28. So I guess we're going to have to throw it to the class to vote who should get the candy. So if you think your reps really should win this and you should get the candy, make some noise. If you think your TAs should get the candy, make some noise. All right, so you get the candy, so why don't we, here, help pass out the candy here. We got plenty of bags and baskets. Take it all up on both sides and pass it out. Okay, is everybody getting some candy up there? We should have enough for everybody unless somebody got really hungry down here in front. Okay, so while you're doing that, let's try to prove this theorem. So the theorem is that all strategies for the n-block game produce the same score. It wasn't a coincidence for 8. And the score, we'll call it S of n for the n-block game. So for example, we're going to try to show that S of 8 was 28. So what strategy do you think we're going to use for the proof? Strong induction. So we want to write that down, proof by strong induction. What's the next step in a proof by Any kind of induction. Base case, not yet. The predicate. What's the predicate here? All right, so, the inductive hypothesis, the predicate. Any guesses as to what P of n is going to be? What's that? Yeah, but that's part of it, but we're going to use this as a predicate to start with. You've gone a step ahead there. So I'm going to start with this as being the predicate, because I'm trying to show they're all the same, and I haven't figured out what the score is going to be, but I think you're already on a good track here for what the score is going to be. Now we do the base case. So we take n equals 1, the 1 block game. S of 1 is 0. We never took a move. We never got a score. There was only one block. We ended before we started. So that's OK. And now we have the inductive step. And here we get to assume P1, P2, all the way up to Pn to prove Pn plus 1. And so now we look at n plus 1 blocks, because that's where we're starting. So we have n plus 1, and we split it somehow. And it could be any split. We might have k on one side, and then n plus 1 minus k on the other side for any k between 1 and n. And let's figure out our score for that scenario. Well, we get the product of these numbers for the first step. We get k times n plus 1 minus k for the first step. And then as we recurse and we split up that block of k blocks, how many points do we get for splitting that all the way down? P of k, because that's the induction. We can assume that as part of the induction hypothesis. And how much points do we get for splitting this stack all the way down? Yeah, P of n plus 1 minus k. And do you see why strong induction is coming in handy here? For the TA strategy, k would be 1. We know P of 1 is 0. And you would just need ordinary induction. This would be P of n. But for a general strategy, it could be any split. So we need to have all these assumed here. Makes it much easier when you're using strong induction. All right, so this is our total score for the game for n plus 1 blocks. And we're trying to show it doesn't depend, it just depends on n. And then it doesn't depend on k. Does that depend on k? Well, it looks like it to me, right? I got k in every single term. So I'm not there. I'm stuck. You see why I'm stuck? Because I'd like to be able to say that the score I get for the n plus 1 block game, this is Sn plus 1, is the same for any sequence of moves. It doesn't even depend on k. But I can't do that. What do you do when you're stuck with an induction proof? What's one of the tricks?
Make it stronger.
Make it stronger, which means I get a stronger induction hypothesis. Now, somebody gave me one up there before. How could I strengthen my induction hypothesis here? Give the formula for Sn. That would make it stronger. I tell you what it is. What's a good guess for the formula here? Factorial. Well, is S of 8 factorial? Nah, not so good. Yeah, that's a better guess. Equals n times n minus 1 over 2. And in fact, what 8 times 7 over 2 is 28. It works here. Let's check another one. What's S of 2? 1. Well, 2 times 1 over 2. Ooh, it works. What's S of 3? 2 the first move, then one more. It's 3. 3 times 2 over 2 is 3. Ooh, it looks good. So now I've got a stronger induction hypothesis. Not only is it always the same, it is that number is your score. Let's see if that works. Let's plug that in now. So base case, let's check it out, is 1 times 1 minus 1 over 2 equal to 0? Yes. All right, let's plug it in here now. Well, P of k would be now k minus 1 over 2. This would be n plus 1 minus k, n minus k over 2, plus this one here. All right, I got to add all these things up and see if it equals that expression for n plus 1. Let's do that. All right, I get 2kn plus 2k minus 2k squared. I'm putting all this over 2. One giant mess over 2 here. Plus k squared minus k. Yikes. Plus n squared. Well, let's write it just as n plus 1 times n. All right, minus kn minus k minus kn. All over 2. And now let's cancel. 2 kn's here, cancel kn, kn. 2k cancels k and k. 2k squared, minus 2k squared cancels k squared. Oh, and I forgot plus a k squared from here and here. So I'm left with n plus 1 times n over 2. That is Sn plus 1. And the k disappears. We've established now the stronger induction hypothesis. So not only did we prove that every set of unstackings gives you the same score, we proved the score is, for n blocks, n times n minus 1 over 2. All right? Well, that's pretty good for strong induction. Lets you do some pretty powerful things. OK, very good. That's it for today.